All right, can you guys hear me now? All right, yay, all right. So I had to dial in on the phone, of course, LCPS technology, fail blog right here. Let's see what we got going on. All right, so let's go ahead and share the screen here. And then I don't know if I can hear you guys or not. So somebody, I guess, go ahead and say something because I want to see if I can actually hear you guys at all.
Hi.
All right, so I just hello, yes, okay, everybody's there. So you guys can hear me okay now, right?
Yeah.
Yeah, hey, Ashley, how are you? Hi, Elizabeth. Good morning, Aditi. Hey, Eric. Hopefully you got your microphone sorted out and all that's ready to go. But if not, just go ahead and type something there in the chat window, and then we'll go ahead and kind of work with it that way. So let's make sure, let's see, this part up here. Let's see, so audio, video. I just want to make sure it's being recorded. Let's see, pause recording. Yay, okay, it's recording. Cool. All right, so here's one of the questions. I'm not sure who posted this one. So let's check this one out here because somebody asked about, you know, what's the maximum of the derivative on one of their test questions. So with this one, this question is really interesting because it's asking you not just the max of the original function, but the max of the derivative. So with that, you have to be really careful, and you can kind of see over here on the right-hand side what I've got written out on it, f prime of x equals 6x minus 3x squared. So you find the second derivative and find its only critical number, which in this case is 1. And then when we go ahead to see the intervals of increasing and decreasing, that's actually where f double prime is positive or negative. That's actually talking about the maximum of the first derivative. So we get that little x value, and we're like, okay, yes, we have a max because we change from increasing to decreasing at x equals 1, and then we plug that 1 into the first derivative function, which will give us the maximum. And the maximum is always going to be the y value, not the x value. Where it occurs is the x value, which in this case would be x equals 1, but the y value would be, but the max would be 3. So I hope that answers that question, whoever had that one, so they can go ahead and do that. So that was that question, but what other questions do you guys have coming up with all for your quarter test? So does anybody have any questions? And if you can't get your audio to work, just go ahead and type your question in the chat. And you can get to the chat just by going up kind of to the top of your screen, and then go to you'll see chat right there, and then you can go ahead and do that. Ashley, you got anything? Let's see, can we go over EVT? Yes, the EVT, okay. So the extreme value theorem. So when you look at EVT, what does the EVT actually ask you for? So what is the purpose of the extreme value theorem? Does anybody have any idea on that one? Yeah, very good. Yeah, who typed that? Aditi, yes. So you're going to find absolute maxes and mins. So we'll do our first derivative like we normally would, but with the extreme value theorem, not only are you going to include whatever critical values that you get for that particular piece, you're also going to look at, I call it team endpoint, but you're going to look at the x, or you're going to look at the x values that your function is kind of talking about here. So, ooh, let's see if this works. Yay, it does. All right, cool. So let's add a page here. So if you had, say, f of x equals, and we'll just keep it simple here, 3x squared minus 5x in the interval -1 to say 3. Actually, we're going to make it 6x. Yeah, we'll make it 6x just to make that a little easier. And say you have that interval right there. So the first thing we want to do is the function continuous and differentiable within that interval from -1 to 3. And of course, it is because we've got a polynomial. So we look here at f prime of x, and we're going to get, let's see, 6x minus 6. And we set that equal to 0. So if you move the 6 over, we'll get 6x equals 6, and then x will have a value of 1. So the points that I'm going to test for this, because depending on if you're looking for a max or a minimum, we only have one x value here. So we would test 1 into either this part right here, into the derivative function, or sometimes some people might kind of think about it like this, 6 times x minus 1, and see if you put a number in on the left side of 1, what sign would you get? And if you put something on the right side of 1, what sign would you get? So if we put in a number like 0, 0 minus -1 is -1 times 6. So your first derivative would be negative, which means that my function is decreasing. And then if I put a number in on the other side of 1, I would get a positive value for the first derivative, because 2 minus 1 gives me something positive. When I times that by 6, I get a positive value. So, so we have that. And then so right here, I would have a minimum. But yeah, so Rhea, yes, your question is right on. So, so 1 is one of the values. So what I do is I then test 1, or I plug 1 in. So 3 times 1 squared minus 6 times 1. And that gives us 3 times 1 minus 6, we get -3. And then team endpoint here, so we're going to test -1. We're going to also find the value at 3. And you do that in your original function. You do that in your original function. And when you plug that in, so 3 times -1 squared minus 6 times -1. So, and then when we plug in 3 times 3 squared minus 6 times 3. So when we get those values for that, then we just kind of take a look at the function and say, did they want a max or do they want a min? And the biggest of those values would be the maximum, and the smallest of those values would be the minimum. So does that make sense? Yeah, so Aditi, let's see, your question is, when asked to find the relative and absolute extrema, how do you differentiate the relative extrema from the absolute extrema? All right, so relative extrema, you don't include the endpoints. You don't include the endpoints. And absolute extrema means you're generally going to be looking in a specific range of x's, or within a certain interval for your x values. So like in this case, we'd be looking from -1 to +3. If I wanted to know the absolute minimum on that, then I want to see which function, make sure that there's no y values any lower than the y value that we have. Does that make sense? Yeah, it does. Okay, cool. Awesome. So does that clear up EVT a little bit for you? Yeah, so yeah, you would have to test only 1 if you're looking for maximum, a relative max or a relative min. Very good. All right, so let's see, who else has a question going on? All right, that's awesome. You're welcome, ADD, anytime. What other kind of stuff you guys have questions on? Or if you have a, linearization. Wow, I can't hear you guys. So thank you for typing that in. So yeah, so if you have a question, because I don't think you guys are muted. So if you have a linearization, yeah. Linearization. All right, so let me pull up one of our old test questions on here, and then that way we can kind of take a look at that. So let's see, where did I put those? Boop. Let's see, we're gonna go here. And then, because linearization, anytime you're linearizing something, you're going to do an approximation of the, let's see, quiz test right here. So let me see which one. Applications, was it on this one? Then we do the linearization, critical points, continuous function, Linearization, no. All right, so nope, not that one. All right, so miscellaneous unit. I think it was in there. So it's negative, inverse functions. Oh yeah, so let's take a look at this guy right here. So when you go to approximate a value, so let's kind of take a look at this piece right here. We're going to take a look at question 11, and let me just take a little snapshot of this, and we can put this in and talk about it a little bit more in this little guy over here. All right, so go to page, and let's add this. So with linearization, you're going to try to come up with an approximation for a particular line. And the line is going to be given, you're going to have a certain equation. And one of the things you always want to do is kind of look at the equation. In this case, oops, we're not going to use that. In this case, we're looking at the square root of something. So our general function that we're working with here is y equals square root of blop. And in this case, our blop is 4 plus the sine of x. Now, that's going to be our original function, and we're trying to estimate it at this y value, or this x value right here, and take a look at what is that value approximately. So when you do that, so anytime you need a tangent line, whether it's an approximation, you always need two things, and those things are a point and the slope. Always, always, always. So you need a point and a slope. Now they tell us in the original problem, like, hey, our x value is 0. So we know it's 0 something, and then we have to figure out what the y value is. And to figure out the y value, you just take whatever the function is they give you, which in this case is 4 plus sine of x square rooted, and we have to evaluate that by plugging in 0, the x value that they give us. So when we do that, and again, this is like why the trig never dies. So if we plug in 0 into our sine function, we would know, of course, that the sine of 0. And again, if you get stuck on it, you can kind of think, remember, 0 is over here. So that'd be at the point 1, 0. And if you want sine is going to be your y value. So sine of 0 is going to be just 0. So then you're just looking at y of 0 is going to be square root of 4, and we know that that has a value of 2. So our y coordinate is 2. So does that make sense so far? How we got our point 0, 2? And somebody can just type a yes in there since I can't hear you. All right, cool. So thank you. All right, so that's the point part. So we have our point. Now to get the slope, we're going to take that original function that we have, 4 minus sine of x, and we're going to find its derivative. We're going to find the derivative. And be careful. And this is why anytime you see the square root function, like try to write it as the exponent instead of just having like square root of whatever. Write it as an exponent so that way it's a little bit easier to work with, because then you bring the 1/2 down when you take the derivative. And then you've got your inside function, 4 plus sine of x, subtract 1, and that gives us our new exponent of -1/2. But then be really super careful. Don't forget to take the derivative of the inside piece. So that's chain rule. And the derivative of 4 plus sine of x is cosine of x. Now, once we get that derivative, and you don't have to simplify or clean everything up, you can just leave it in factored form. Since we want the y value to be, or our x value to be 0, so we're told what that x value is. So anywhere there's an x, we're just going to plug in a 0. And again, here's your other piece on the unit circle, cosine of 0. So again, we've got the point 1, 0. Cosine is my x value, so that's why cosine of 0 is just 1. And then the 4 plus 0 piece, we already did that one before. And when we square root this, and this is where sometimes people might make a mistake, because your exponent is a -1/2. So when you would normally square root 4, you're like, okay, that's just 2. But if we're taking the square root of 4 and the exponent is negative, then that's going to be 1 over the square root of 4, which is just 1 over 2. So that's why this guy right here is just square root of 2, or 1/2. Now, after that, we just get, we find that product and we get 1/4. So that gives us the other piece that we need. We get our slope. Is that part okay? So we have our point and our slope. So Rhea, are you good with that so far? I guess type in another yep if you're good with all that. Awesome. All right, cool. Now comes the fun part. And with this piece, so we have our point and we have our slope. So generally speaking, we're going to use this equation. Y minus y1 equals m times x minus x1. Now, in the x1 and y1 parts, so these guys right here from our point, they're going to go in here and right there. And then our slope of 1/4 that we just found, that's going to get slid in for our m. Now, whatever the x value is that we're trying to approximate, whatever that x value is, that's going to go, which in this case is 0.12. So 0.12 is going to get substituted into the x value of the thing that we're trying to approximate. So this could start out y minus 2 equals 0.12 is our x value, and our slope is 1/4. So we'd have 0.12 and then minus 0. So minus 0, we don't really have to write that, but you could if you wanted. And then generally speaking, and then we've got to kind of clean this up, because if we're trying to approximate a value, that means we want to know what y is, because that's the only variable now we don't have. So you can move the 2 over, and here's kind of another way to pay attention to some things here. Anytime you see this phrase approximate, that's right off the bat, that's a squiggle alert, because you're always going to approximate. And so when you write that mathematically, you're going to have the little squiggles right there. So we move the 2 over, and 2 plus, and then 1/4 of 0.12. Now, all of these kinds of problems that are non-calculator, whatever your slope is, will be divided. So we get 2.03. Ooh, great. Unstable internet connection. Ha! I guess that goes along with the unstable audio connection. All right, so that would be the approximation for this one, which in this case was, choice B, 2.03. So does that help, Maria? Are you good to go with that, or anybody else that had a linearization question? Okay, cool. Awesome. Yeah, glad I could help you out with that. So who else has got a question? And just go ahead and type that in the chat window, since apparently the audio is kerplunk. I have a question about a past test question. I'm putting on the, oh, you're going to put it on the Google slide? Awesome, thanks. So I'll go back to that, and we will see you put it on the slide right as we are waiting here. All right, so that's awesome, and I appreciate you doing that. And same thing, Rhea, I think I shared the link with Miss Harris and Miss Littlefield both. So if you have a question of something, you can take a picture of it and upload it to that slide, and then that way, I think they posted that in Google Classroom. If not, text it to somebody else, and then you can we'll get that up there for you. All right, so Aditi's working. Let's see, what's that one? So the graph, oh, I love this question. This question is so cool. Can you type in the chat window which test that one's from? Because I forget which one that is off the top of my head. I want to make sure I pull up the right one. Because I know, oh, that question you see actually a lot. That's was that on the Quest? Oh, the applications of derivatives test. All right, cool. Applications. All right. So with this question, all right, and you see these, you'll see these guys here a lot with this. So with this one, you're going to kind of break it down into 3 things here, and you're going to have to kind of come up with, in some cases, we'll be able to come up with a number, and then you're like, okay, and other values we're just going to have to call as generally being positive or being negative. So when you have your, with this, the first thing you have to do is make sure that you read the question, because very common mistake with this type of question, and just about every year on a multiple choice, you'll see something like this with that. So with this question, you're going to kind of analyze 3 things with it. All right, so let me move this over here just so we can see it, because we're trying to figure out, like, hey, which one of these is the biggest? Now, when you read this, the first thing this says, oops, is that this is the graph. Come on, there we go, yes. All right, we'll do another one here in a minute. So when you take a look at this, we're talking about the derivative. So this function right here, and they'll also put it right there. So that's the graph of the derivative. Now, so the derivative is at 2. So if I look right here at that x value, I know that that's the value of 2 for my derivative has a value of 0. Now, if I take a look at my second derivative, so if I look at the second derivative, that's just basically the slope. And the slope right there at 2, that's going to be a positive slope. So does that make sense so far that that's a positive slope for that piece? That's going to be that guy right there. All right, so you're good with that now, Aditi? All right, so I know that my second derivative is positive. I know my first derivative at 2 was just plain old 0. And then to figure out what sign, because we don't have a function or anything, what I have to look at is actually this little piece right here. So if you think about the x-axis, all right, so there's our x-axis right there. Everything that's on the top part, so I'm just going to highlight that yellow. Everything up here on this side of our x-axis is positive, and everything that's on the other side of the x-axis is negative. All right, so when I look at 1, when I look at the x value of 1, I could say, all right, 1 would have to be somewhere down here, but also look at this other piece of information that they give you in the stem of the question. This is given. So the information that you're given is also, it tells you it has a y value of -2. So if I know my x value is -2, like they just tell us that. We don't really have to do a lot of analysis for that. So once I kind of look at that, I'm like, all right, so f of 1 is -2. So f of 2, whatever that is, f of 2, I know that that value, because 2 comes after 1. And everybody okay with that? So if I'm thinking about a number line, like here's 1, here's 2. Now, if I look at my, the part that's highlighted here in blue underneath, my y values down here, below the x-axis, those are all negative. So if I know my y value is going to be negative, and we're told that f of 1 is -2, so say that's -2, and the value for f of 1, right, f of 1 equals -2. If I have a positive slope, then this guy right here, I'm going to be kind of going along with that. So you're just analyzing which one is 0, which one's positive, which one's negative with that. So that's where you always kind of come up with those. Does that make a little bit more sense now, Aditi, how to put those pieces together? Yeah, it takes a little bit to do that. You'll see that kind of problem just about every year on a multiple choice part. They'll either give you the graph of the derivative. Sometimes they might even give you the second derivative graph, but usually it's a derivative graph that they give you a function of, and they want you to evaluate it. And so the key thing is when you read this part right here, to take a look at that piece right there, and the reason that I know, let's see, what else do we have? F of 2. All right, cool. So let's see, we got about 5 minutes left. So go ahead and either type something else in. Any questions that you guys have or anything, so we can go ahead and get that sorted out for you. And then can we go through a question on concavity? Yeah, that's a great, like, what do you want to know about concavity? Can you be a little more specific, like how to tell where a function is concave up or concave down? To put it into slides really quickly. Oh, you're going to put it in Google Slides. All right, cool. So let's see. So we're going to put that one there. Awesome. All right. How quickly can we get that put in there? Let's see. All right. Thanks, Adiba. All right. Oh, yeah. Second derivative test. So while you're putting that in the slide, remember that one piece where we talked about the justifications? Now, you can use a second derivative test for two things. One is to prove whether a function, where the intervals of concavity are, where a function is concave up and concave down. But you can also use it to prove maxes and min. Aditi, are you looking over the justification piece? Oops, let's see, let's go down here. So there's going to be a little bit of stuff in there, increasing, decreasing, proving max, min by a second derivative test. So when you do that, what you're going to do is you're going to get a critical number from the first derivative. And you take that critical number and you're going to plug it into the second derivative function. So in this example here, we've got x equals 3, and 3 is going to be our critical number. So when you take the function, which in this case, we don't know what the actual function is, we're just using this as an example. You're going to write these two things, since f prime of 3 equals 0 and f double prime of 3 is less than 0. If that's the case, then you're going to have a max. And if you think about it, when a function is concave, when a function's second derivative is negative, that means it's going to be concave down. So if you have a function that's concave down, then that means, oops, there's concave up, here's concave down. If you have a function that's concave down at a particular x value, then that x value is going to be a max. But if you have a function that's concave up at an x value, and these x values are your critical numbers from your first derivative test. So you're taking those values and plugging them into the second derivative. And then I think we had a test question like that, just processing what to plug in for the test. All right, cool. And I think, let's see, so let's take a look at this. Say you get f prime of x equals 4x minus 8. Let's see, yeah, we'll do that. Or actually, no, we'll do one like this. F prime of x equals x squared minus 2x minus 3. So that would factor into, let's see, or x minus 3 and x plus 1. So we'd set that equals 0, and we get these two values, x equals 3 and x equals negative 1. So now the thing I'm going to do next is take the second derivative, and if I look at my first derivative function, x squared minus 2x, I would get 2x minus 2. And then what I'm going to do is I'm going to evaluate the second derivative at 3 and the second derivative at negative 1. Now, if I plug 3 into here for my x, 2 times 3 is 6 minus 2 is 4. That number is greater than 0, which means since 4 is greater than 0, that's going to be concave up. So that also tells me that if I'm concave up, that it would be this guy over here, concave up. So that would be a relative min. And then if I plug in negative 1, 2 times negative 1 minus 2, I get something negative. 2 times negative 1 minus 2, I get negative 3, which is less than 0. So that's going to be concave down. So the way you would explain that, the way you would explain that is you'd write this big old long phrase. Since f prime of 3 equals 0 and f double prime of 3 is less than 0, let's see, there is a relative. Now, if you're concave down, you're going to have which one, a max? Or yeah, you're going to have a relative max because you're concave down. Relative max at x equals 3. And then you'd write a similar kind of phrase for the other one being a relative max at x equals, at x equals, let's see, since f prime 3, we're concave up. Yeah, so that'd be a relative min. See, and that's the other thing too. Make sure you look at the right piece of it. We'd have a relative min right there. There'd be a max at x equals negative 1. So does that make sense? Yeah, x equals negative 1 would be a max because you're concave down. So does that help? Oh, you added your question to the slide. Yay. Okay, let's see. All right, so let me go back to the slides here and see what our question is. Oh, the product of the two negative integers? Yeah. So this guy, so there's a couple of things in here, and let's see, was that our last? No, that wasn't this quest. That was our quest. So when you take a look at the product of two integers is 1225. you're going to kind of set it up two ways. Because we're going to have a product that we're going to have to pay attention to, and that's we're trying to find the minimum sum. So I just use generally the letter S to